Hello, welcome to Chapter 5, Section 4. We are continuing with our normal curves today, talking about sampling distributions and the central limit theorem. So first, we've been using normal curves to calculate probabilities and the area under the curve. So today with our sampling distributions, we're just kind of adding another thing to them. So sampling distributions just occur when we are taking samples of a certain size. And so once we're dealing with a sample size and looking at the averages of just that sample, then we're dealing with normal curves that are slightly different because the spread, the standard deviation, is going to change a little bit whenever we deal with sample sizes. So the main difference between our problems from before and now in this section is that they're always going to tell you a sample size. So because the standard deviation is changing, it's now going to be called a standard error. So anytime we're given a sample size in the problem, we have to use standard error. And the formula looks like this. It's sigma over the square root of n, where sigma stands for the standard deviation of the population. So that's something that should be given to you in the problem. N is going to stand for your sample size. So whatever size they tell you, that's what you plug in for n. The mean is going to be the same as the population, so the mean doesn't change at all. So again, the mean should be given in the problem. And then lastly, the shape of the sampling distribution, we want things to be that normal shape, that normal curve, because otherwise we can't use the table to find any of our probabilities or the area under the curve. So basically, we can only do these normal curve problems when the sample size is large or when the original population shape is normal. Because when we have a small sample size, and when we say small, like n is less than 30, so then the shape of the sampling distribution is going to match the shape of the original population. So if the original population is normal, then we're good. We can still use the normal curve and the table and all that good stuff. But if the original population was like skewed left or skewed right, then our table wouldn't work anymore. But if we have large sample sizes, like n is greater than or equal to 30, that's considered large, then the central limit theorem says the shape will be normal, that normal curve shape, even if the original population shape was not. So even if it was skewed or whatever, as long as your sample size is large, it'll end up normal. So that's kind of cool. And so we use the central limit theorem a lot for that. So let's do a few examples. First one, cellular phone bills for the residents of a city have a mean of $63 and a standard deviation of $11. Random samples of 100 cell phone bills are drawn from this population and the mean of each sample is determined. Find the mean and standard deviation of the mean of the sampling distribution, then sketch a graph of the sampling distribution of sample means. So anytime they mention sampling distribution, they're talking about the thing with our new formulas, the standard error, because they're giving us a sample size. Because right here, they tell us random samples of 100 cellular phone bills. That's our sample size. They told us it was a random sample. They're using 100 at a time. So in this problem, n is going to be 100. The mean, they told us, was 63. And so the standard deviation, instead of just using the standard deviation that they gave us, we're going to need to calculate the standard error. So the standard error is going to be the standard deviation that they give us divided by the square root of our sample size, and our sample size was 100. So when we do this, we end up with 1.1 as our standard error. So that's going to be our mean and standard error of the mean of the sampling distribution. Sketch a graph just means it's going to be normally distributed because we have large sample sizes. Our sample size is 100. So even though the original problem doesn't say anything about what shape it is, because we have large sample sizes, we can assume it's going to be random or normal. So our mean, I'm going to label with 63, and our standard deviation, or our standard error, is 1.1. And there we go. For this next example, we're going to do something similar. This time, the training heart rates of all 20-year-old athletes are normally distributed with a mean of 135 beats per minute and a standard deviation of 18 beats per minute. Random samples of size 4 are drawn from this population, and the mean of each sample is determined. Find the mean and standard error, then sketch a graph. So this time, they're telling us n equals 4 because they told us random samples of size 4. So right off the bat, we know our sample size is small. This is less than 30. So keep that in mind. Our mean is going to be the same as whatever they told us. So if they told us 135, and the standard error we'd have to calculate. So the standard deviation was 18 divided by the square root of our sample size, which was 4, is going to end up being 9. All right, so when I sketch this out now, I want to see if it's still going to be that normal shape, because we have a small sample size, so we can't use the central limit theorem. The central limit theorem only works for when your sample size is large. But in this problem, they did tell us that things are normally distributed. So if they're saying that it's normally distributed, they're saying it's already normal, so we don't even need that large sample size. So when I sketch a graph, it's going to look like a normal curve with a mean of 135 and a standard deviation of 9, or standard error of 9. And we said it was going to be that normal shape because they already told us normally distributed. All right, so in this next example, let's actually start finding our probabilities then. So this time the graph shows the length of time people spend driving each day. So if we look over here, you randomly select 50 drivers age 15 to 19. So in our sample, we're using 50 drivers. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Assume that sigma, the standard deviation, is 1.5 minutes. Okay, so first, we have a large sample size because n is 50 for us. So that means we know it's going to be a normal shape, and then we need to figure out the mean and the standard error. So the mean we can find using this graph that they tell us to look at, because they're asking about ages 15 to 19. So that would be this first car right here. For ages 15 to 19, the average time spent driving each day is 25 minutes. So they're telling us the mean is 25. Our standard error is going to be found using our formula. So they told us the standard deviation was 1.5. And we're going to divide that by our square root of our sample size of 50. When I do that, I end up with 0.212. So in general, standard error, we want a little bit more accuracy, so at least 3 decimal places is better. Okay, then they're asking for the probability that the mean time they spend driving each day is between 24.7 and 25.5. So if I were to draw this out in my picture, it would be somewhere, 24.7 would be somewhere to the left of 25, 25.5 would be somewhere to the right. And so we're basically calculating an in-between area. So remember, in-between is when we find the z-scores for each of the numbers and then subtract the two areas from the table. So let's find the z-score for the bigger ones first. So 25.5 minus the mean of 25 divided by the standard error this time of 0.212. And then I'm going to do the same thing for the 24.7. I end up with z-scores of 2.36 for the 25.5 and negative 1.42 for the 24.7. So now we need to use the table to find the percentages that go with each of these z-scores. For the 2.36, if you use your table correctly, you should be getting 0.9909. And then for the smaller one, the z-score of negative 1.42, we end up with a percentage of 0.0778. So remember, since this is an in-between area, we're just subtracting the bigger minus the smaller, and we end up with 0.9131. And that's the probability that the mean time they spend driving each day is going to be between 24.7 and 25.5. So this part right here, this is basically us finding the areas like normal. It's just this whole process, we just have to find that new standard error first. Otherwise, it's the same stuff that we've been doing. All right, one more example just to really make sure we got this. So this time an education finance corporation claims that the average credit card debts carried by undergraduates are normally distributed. So, oh my goodness, right there, they're already telling us it's a normal curve. Mean of $3,173 and a standard deviation of $1,120. For part A, what is the probability that a randomly selected undergraduate who is a credit card holder has a credit card balance less than $2,700? Okay. So in this question, notice that they didn't give us a sample size. So like in this original part of the question, in part A, when they're asking about the probability, they don't tell us a sample size. If they don't tell us a sample size, that means we don't have to do the standard error formula. That means in our normal curve, our mean is still 3173 that they told us. The standard deviation, if they don't give you a sample size, is just whatever standard deviation they told you, so the 1,120. And then they're asking for less than 2,700. So 2,700 would be to the left of 3,000 whatever. And we're shading to the left because they're asking about less than. Okay, so let's find our z-score. When we do that, we end up with negative 0.42. And then remember, this is an area to the left, so I just need to look up the z-score in the table, and then that's my final answer. So I end up from the table with 0.3372 when I look for a z-score of negative 0.42. And that's my probability. In part B, it says you randomly select 25 undergraduates. So right there, they're giving you a sample size. They're telling you n equals 25. So now your mean is still the same number, but the standard error is what you have to use now. So now we have to calculate that $1,120 divided by the square root of n, which is 25 for us. When we do that, we end up with 224. Okay, so this time, my picture's still gonna pretty much look the same. My mean is the same, my standard error is now 224, but I'm still looking for less than $2,700. So I'm still shading the same direction and everything. So this time when I find my z-score, I just have a different number for the bottom of the fraction. And when I do that, I end up with negative 2.11. In the table, a z-score of negative 2.11 ends up with a percentage of 0.0174, or 1.74%. Okay, so I wanted to show you, because we're dealing with a sample size now versus before when we didn't have a sample size, the probabilities change a good amount. And so that's why we kind of, it's usually better to have that sample size because we're more accurate when we have larger sample sizes. So that's why our probability is smaller. Okay, so that's it for this section. Thanks for watching. Don't forget to like and subscribe. Bye!